Okay, welcome back. So I'm gonna start by finishing what we ran out of time for last time, and I think actually thematically it goes very well. These topics sort of go very well together. Compared to the original calendar, I kind of put Lyapunov more into Tuesday, and I'll finish up the PFL today. So sorry, the calendar was. I improv'd a little bit on the calendar, but I think we're basically back in sync. So last time we talked about Lyapunov a lot, and then we talked about a simple controller for pumping up energy of the pendulum and getting it to the top. And as we were ending, we started talking about how you're going to do that for the cart pull. And I want to finish that story today, but I want to make sure the bigger idea comes out. And the big idea that we started with was partial feedback linearization. And that's actually kind of closely related in an important way to a different idea called differential flatness. So that's the big theme today here, is that, roughly speaking, if you have n degrees of freedom and you have m actuators, you get to control m things. Okay? We're going to try to make that formal. Certain conditions have to apply to make sure that those m things you've chosen are controllable, are coupled to your actuators. But there's a couple different ways that manifests and gives us the ability to write controllers or write planners. So were just working on the partial feedback linearization of the cart pole. Okay, and the first thing that we observed was this idea of co-located partial feedback linearization, which means wherever your motor is, if there's a degree of freedom attached, with a motor attached, you'd like to be able to linearize that degree of freedom. And so for the cart pole system, since there's one degree of freedom, which is x, which has the motor, the pushing directly attached, it's not too surprising that we were able to say, change the dynamics into x double dot is whatever we'd like, x double dot desired, right? And we were left with theta double dot doing something funny. I could write it down here, but it was, nonlinear, right? So if we choose, and the intuition there is that if we have the model, we can compute with the dynamics the effect that the pole is having on the cart. And then we can just apply exactly the equal and opposite forces to cancel that out and make the cart go back to simple dynamics, right? So this thing, as it swings, is going to push and pull on the cart. By default, if force was 0 and this thing started swinging, the cart would go boom, 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 responding to the pendulum. You can apply exactly the opposite force, cancel out the effect of the pendulum, and you feedback linearized one of the degrees of freedom, right? And the remaining one is still nonlinear. The other idea there was non-collocated. Partial feedback linearization, where we said, actually, most of the time, you can control the pendulum, if you'd like. You could say theta double dot equals theta double dot desired. You're left with x double dot is something nonlinear. But it doesn't actually work all the time. In particular, we saw in the simple equations we wrote that it failed when the cosine went to, the cosine in the denominator went to 0, my controller blew up, and that was equivalent to whenever the pole was exactly horizontal, because nothing I can do with the force instantaneously could affect the dynamics of the pole. Okay? This one maybe isn't so tragic. If you let it just wait a second, then it's going to fall down and you can control it again. But a lot of the controllers we choose to write around this have this nasty property that, the ones we were tempted to write last time and we'll finish looking at here, you have to be careful because even if it's not here, maybe it's here, if you write a controller that's trying to control it, the forces you would like to apply in order to stabilize this might go to infinity, as there's like a singularity there that would be, your naive control laws are going to blow up. Okay? So what I want you to see today, instead of writing the specific equation for the cart pole, I want you to see that this is a general idea. And actually, this notion of coupling is a general idea too that we can understand in its almost full generality. Okay, so our favorite manipulator equations here. Right, so in general, this thing lives in Rn by m. Are the symbols I typically use for it. This is the number of degrees of freedom, our number of joints, and this is the number of actuators. Okay, a lot of the times when we've written it down, B was basically 1 for a bunch of the variables and 0 for the other ones, okay, or identity and 0. So let's use, I'm going to write the partial feedback linearization, assuming only that, just because that's a common case and it makes all the equations a little bit easier. So let's assume that my Q variables here are grouped into two groups. You can reorder Q however you like, of course, right? Let's say you've just happened to reorder them in such a way that all of my actuated joints are here. My co-located joints, the ones that have a motor attached, I'll put those all at the bottom, and I'll put all my passive joints at the top, okay? So that means we can look at this equation a little bit differently, zooming in on here. If I think of M of Q as this matrix, I'll write it like that, even though it's, okay. I'm going to not write the function of Q every time, just to save myself some writing, but remember M is always a function of Q, okay. Then I can write this equation taking advantage of that form as M11 Q1 double dot plus M12 Q2 double dot plus a bunch of stuff. You know, I'm going to just stick this into some general torque that applies to 1. Oh, that's my passive one. I said there's no U's over here. And then 2, 1, Q1, M22, Q2 equals tau 2 plus my U vector. This also depends on, this depends on Q, this depends on Q, this depends on Q and Q dot, right? These are all the dependencies. I'm just going to keep it short. But I said in the simple case where I've got actuators on some joints but not on the other, I get equations of motion that look like this. Okay? Remember we had some nice properties because this was the mass was the energy, right? It's a mass matrix. And the total kinetic energy is 1/2 Q dot transpose MQ Q dot. So we sort of understand that M is positive definite. Conveniently, that also implies that M11 and M2 are positive definite. Okay? These we don't have any guarantees about. The coupling terms, the cross terms, they might not even be square, right? Okay, but we happen to know this is good and this is good. Okay? Okay, so now in this more general form, we can think, what does co-located partial feedback linearization mean? It means I'd like to control, let's see, Q double dot 2 using U, right? And I can write that in its full glory here for any manipulator pretty easily, right? So the way I do that is I have to solve away Q1 double dot, get rid of that. Right, so let me solve that away here. Q1 double dot equals tau 1 minus M12 Q2 double dot. This whole thing times M11 inverse. Make that a little bigger. And since M11 is invertible, that's okay. A little bit clearer. I can stick that back in here, okay, and now say M21 times that whole shebang. Actually, if you group the coefficients of in front of Q2, you get this thing that some of you might recognize as a Schur complement. M21, M11, M12, Q2 double dot equals some other stuff. Okay. That's also invertible, because just by nature of being a Schur complement. But if Schur complement is not in your vocabulary, just trust me that it's invertible. This is something that happens with positive definite matrices often. It's a nice thing. Okay, which means that I can easily now write a controller which just does this. You know, subtracts away this, multiplies by this, and because this is positive definite, that implies that Q2 double dot equals Q2 double dot desired. Right? If you want to know what I was talking about, I just said Schur complement. It's also, that whole thing is going to be greater than 0 because these two were good. Okay, so in the general form, well, pretty general, I did assume that the actuators were simply coupled, that there was, motors applying directly to some joints and not the others. But up to that simplification, this is a pretty general form, and it says that always, in this form, always, this thing is always invertible for all Q, okay? I can look at the effect of my other joints, apply enough torque, okay? I've not given myself any torque limits, so I'm assuming I can command the sufficient torque to subtract out what all the other passive joints are doing to my actuated joints, and make my actuated joints do the thing I want, okay? In practice, you could also just do this by putting a really big feedback gain on something, right? You could just overpower it with high gain feedback. But the model-based way is you look at what all those other forces are, you cancel them out exactly, and you're left with perfect control of the places where you have motors. Yeah? So Asimov, for instance, was doing this, right? So it's walking like this, right? It's doing it with high gain feedback instead of the total model canceling. But the joints where it's got the motors are being controlled perfectly. Right? And it's fighting gravity to do that, but it's able to do that. But, you know, Asimov is very advanced, it wouldn't do this, but there have been robots out there that have proof saying that we're, guaranteed to follow the desired trajectories, but they only talk about the actuated joints. So it could go like this, but then, you go over and it would still be going through its motions perfectly, canceling out gravity, but it might be upside down, right? So it's like, well, if you haven't said something about those joints, which are the center of mass and orientation, then maybe you don't have a proof. You have to watch for that. In the walking world, people say that. Provably stable walking controller, and then they're only controlling Q2. It's kind of a pet peeve. Okay, good? Makes sense. If you know the model, which is a strong assumption, if you know the model, you can always cancel out all the interfering terms with my big motors that are attached to my joints. I'll do it here so you can see both of those. So what does the non-collocated case look like? Now I'd like to say, can I control Q1? Even though my motors are on Q2, right? So to what extent can Asimov control its center mass, for instance? The recipe is almost the same, but just the matrices that end up in these places are different, right? So the same thing. Now, if I'd like to control Q1, then I want this bottom equation to be only in terms of Q1. I need to solve away Q2. Okay, so let's solve that first equation for Q2. Okay, but M12 is not necessarily invertible. Okay, I wrote the inverse there just to start the conversation, but you should immediately say, I don't even know if that's square, right? I could have, what's the size of this matrix, right? This thing lives in R n minus m by m, right? It's the number of passive joints by the number of actuators. Okay, so this could be very small, and that there's no chance of that being invertible. So I'm going to write the pseudo inverse here, which is a least squares solution. This is basically try to do as well as you can given whatever M12 is to being the inverse. Okay. The Moore-Penrose pseudo-inverses. Okay, so that's already one caveat. This pseudo-inverse, just to be clear, so it has a unique solution when the rank of that matrix equals its full row rank here, n minus m. Okay, that's when this thing, when Q2 is completely defined in terms of Q1. And remember, since this is a function of Q, this can be state dependent. For instance, the cart pole, M12, is a scalar, and it's non-zero most of the time, but it goes to 0 here, which is equivalent to this thing dropping rank. It goes from rank 1, which is a scalar that is not 0, to rank 0 when it goes to there. Okay. And the rest follows. If I put that solution down and do the same basic trick, then I'm able to write a feedback linearizing controller. But it's the catch here is making sure that matrix has rank. Okay, and so this idea here, this rank condition is called inertial coupling. And it can be state dependent. You could have global inertial coupling if it works for all Qs. Okay. In general, your controller. So of course, numerically, mathematically, this is a property, a Boolean property that you're either low rank or you're not. Okay. Mathematically, you can get to be more and more closer to singular as your numbers get close to 0, as your eigenvalues get close to 0, for instance, okay? So you'd like to have strong inertial coupling, meaning that this matrix is sort of safely away from 0, okay? And you see that. So for instance, do you remember in the Acrobat, I said that you had to put a mass somewhere. Where did I have to put the mass? If you run the numbers here for the Acrobat, then M12 is a matrix well, it's a scalar in that case, where the number gets very small, depending on it's called inertial coupling. It really is the relationship. It's in the diagonal matrix. It's the mass matrix here, right? It's the diagonal term. You'd like motion in the actuated joints to affect motion in the unactuated joints. It's got a very physical meaning. So in practice, when you're building acrobats, in order to have strong inertial coupling, you'd like that when you wiggle your elbow, your shoulder moves, okay? So what that means is you do a lot of engineering work to make this inertia small, which means in practice we try to put the motors on the base and then run the cables down to actuate the elbow, okay? To keep no actuation, no motors, nothing heavy in here. And then you put a lead mass on the bottom to have a large inertia here, okay? You can also see that in the world of legged robots. So for instance, Raybert's initial hoppers have a large counterweight. Have you seen those before? We're going to do them in a few. I'll just pull it up. I'm going to talk about that controller later, but what could go wrong? Yes. Okay. So make that. Okay, it's no coincidence that some of the first hopping robots put big lead masses out on a weight like this, right? Because, and we'll talk about the details of this later, but they wanted the inertial coupling to be in their favor so that the actuator could control the leg when it needed to and could control doing relatively less control of the body. And we'll see the details of that. But this comes up a lot. And actually, quadrupeds are kind of nice to control because they have long bodies, right? And strong inertias like that. Okay? So, this felt kind of arbitrary, right? So that why would I just happen to want to control my passive degrees of freedom only and not my actuated? It seems like in general you should be able to pick any m things to control. Okay, so for instance, there's not that many options here on the cart pole, but I could, for instance, care about, let's say, the x position of the pole. Okay, let's say the variable of interest is somehow the position of that in space, and I could write a controller that's going, doing whatever it does to make that somehow stay in some position. I guess that's kind of a weird one, right? Because you'd have to, like if you wanted to move this way, you would have to race here to fight gravity, but there's only a few things it could definitely do, right? Similarly, maybe a simpler one would be if you wanted it to drive up and down. So there's a more general form of this equation, which is which introduces this idea of, let's say, a task space variable. Okay. All right. So let's make some new variable z, which could be, for instance, the vertical position of the end point of the pole, or something like this, which is some function h of q. Certainly, if h is just picking off q1 or q2, then that's just a special case of this. But it might be it's more general in the sense that I could do, for instance, let's say in end effector space, I could do the end effector dynamics of the endpoint of the pole. Okay, so then you run the same equations through, and you get this matrix. So if I use h as the gradients of that equation, then I get a big messy thing here, which is h bar. I can still use those same matrices. And inertial coupling is the rank of this general H matrix equaling the n minus n. Okay? So the details are in the notes. I just want you to see that there is, of course, a generalization of this where you can pick any quantities, okay? And based on how those quantities are related to your joint variables, there is a generalization of coupling, of this strong inertial coupling idea, which tells me, is that mapping controllable instantaneously? Okay? And you can pick them off and try to control them. Similarly, in our partial feedback linearization, I could, of course, I can pick things like this to insert the dynamics to be exactly that. I can also add stabilizing terms if I'd like, right? So maybe a slightly better choice of that would be to choose Q2 double dot equals Q2 double dot desired, minus some Q2 minus Q2 desired minus, I flipped my signs here, but. Right, you could put in some sort of regularization or some regulation there to try to feedback linearize that better. Okay. Okay. So we saw this in the specific symbols of the cart pole last time, but it's a general idea. Okay. You have M actuators, you get to control M things, as long as the inertial coupling in its general form holds. So how do we use this to get we're going to combine that now with Lyapunov to get a controller that'll swing the cart pole up to the top. And it's tempting to say, let's use the non-co-located feedback linearization, right? Because I could then just drive, it seems like if I'm going to try to control the pendulum, then I'd like to drive that to the top, and that's the easiest route. Okay, but in fact, that one has this problem that it blows up here, and even if you're close to here, any attempt to strictly linearize theta double dot has to go through that transformation, which gets very numerically bad, and then blows up, and then gets bad. So that turns out to actually not be the simplest recipe. The simplest recipe, which is actually quite elegant, is to use the co-located feedback linearization plus Lyapunov. And remember how we did some algebra to make, I saw a k theta, I'm going to multiply that by another theta to make a theta dot squared, and I made all the terms definitely positive, right? And I'm going to do the same thing here, starting with the co-located PFL for the pendulum. So here we go. So the idea is, let's regulate the pendulum, the pole, to its homoclinic orbit. Using co-located PFL. Because if I've done that, then I'm already controlling the cart pretty well. If I can, while I'm controlling the cart pretty well, I can get the pole up, then it's a pretty simple thing to add a little bit more work to stabilize the cart. So after the co-located PFL, the equations of motion of my cart pole were that my cart was perfectly controlled with whatever my input was. This is my feedback linearized input. And I was left with some nonlinear terms in the dynamics of the pole, right? This is cosine theta, and that's sine theta, right? My shorthand. So the homoclinic orbit was the orbit of constant energy. We're going to just think about the pole alone. I've set all my masses and lengths and gravity to 1, which meant that my energy was theta dot squared minus cos theta. My desired energy for that homoclinic orbit, in this case, is just 1. This defines the homoclinic orbit of the pendulum. And I'm going to use this Lyapunov-like argument where I'd like my energy to be okay. And the way we're going to do that is with our old school nonlinear control hats on. We're going to write the terms down, we're going to manipulate some equations, and make sure that that thing's going downhill. Okay? So the dominant term here is E, so if I call this thing E tilde, then I'd like to know what E tilde dot is looking like. How is my error in energy going down over time? And if I just take the 2 here, theta dot, and then theta double dot, I insert this all in. This becomes theta dot, theta double dot, plus theta dot sine theta. Right, that's just the time differentiation of this. 2 theta dot times the inside chain rule, theta dot times that. Okay? Theta double dot I already know. It's from the dynamics. This is a weird thing. This isn't what physics gave me. This is what physics plus my partial feedback linearization gave me. Okay? But I can work with it. What I'd like is for this thing to be always going downhill, or well, ultimately V dot to be always going downhill, right? So what should I choose? What should I choose to make V dot going always downhill?
E tilde dot, should that just be E dot minus 0 since E dot is 0?
Here?
No, yes. Should that just be E dot minus 0?
Oh, of course, thank you. Thank you. Say it again.
K cosine.
K cosine theta, okay. That's a well-behaved thing. It's not going to blow up on me anytime. That means it gives me a cosine squared. I think I also want to put a theta dot squared in there, or theta dot in there to get a theta dot squared. Okay. But ultimately, this is the thing I want to be going downhill. So I'm going to hit it with an E tilde. I mean, it feels sort of ridiculous game to play, okay? But the result then, if I choose this controller, did I get my sign? Yeah, the sign is actually right. It's weird to say you got a positive feedback there, but actually because of the PFL, I had a negative sign hanging out there. This implies that V dot is K theta dot squared, negative K theta dot squared, cosine squared theta, E tilde squared. Okay? And it's going downhill. It's also, there's an art to picking this, right? You could try to, do divided by cosine theta, for instance. That might be a bad choice, because that one does blow up, right? So there's an art to having controllers that not only achieve this goal of being negative in the Lyapunov function, but also are well conditioned for all theta, that don't depend sensitively on the parameters of the plant, like friction and other things that you don't know, right? So there's sort of this art that went on. Yeah?
This feedback, what is it doing intuitively? This theta dot cosine theta, how is it calculating?
Yeah, I mean, what it's doing is it's killing the dynamics of the cart, and then it's trying to impose onto the pendulum roughly this same pump up energy and then swing around and go, right? So if you were to watch the homoclinic orbit, you would, if you just plotted the pendulum versus the pendulum dot, you would see it drive the system up to this homoclinic orbit, just like our other one did. But to do that, because there's also a cart involved, you have to throw a few more terms in there so that the whole thing works out. Okay? This one, similarly, yeah, go ahead.
So far, the art of choosing Q, and we've only got a couple of them.
Yep.
You've just been squaring everything.
Yeah.
Making everything square.
Yeah.
Are there other ways to do it that are also good?
That is a pretty common one, okay? Mostly because you don't want to divide things out with risking blowing things up. And square things are always positive, right? So it's good. But yes, there is variety there. And in fact, it's often not so trivial. I mean, so the two examples I did, you could by inspection find these controllers. It's often not that simple, right? So if I ended up with more terms here, I also have just a single U that I'm trying to design, right? If I ended up with more terms here, it's going to take more cleverness to get something that's definitely going downhill. This actually doesn't complete the job, because when I run this controller through, this is now X double dot is doing this, okay? So the full story, which I did more carefully in the notes here, you'd actually like to add a few terms into the Lyapunov function, which regulates the cart at the same time, okay? So you can tack on a 1/2 x squared plus 1/2 x dot squared. Throw a few more terms in here, show that it still goes downhill, and you'll simultaneously pump the energy up in the pole, but also keep the cart near the middle, and eventually stabilize at the bottom. Okay? And this one is actually really easy to type in. You have a few parameters that you end up tuning. This K, there's feedback gains on the cart too, but it's very easy to find parameters which stabilize the system in practice. Okay?
Violate our idea that we can only control one state variable with one actuator.
Good. I only have complete control. So I'm doing two things, but I'm not in complete control. I've given up doing complete control of any one of them. So I'm not perfectly driving this along the orbit that the simple pendulum had, right? As soon as I tack in some terms that do this, I'm achieving this almost, but there's some other cross terms. Similarly, I'm not driving like an LQR controller back to the base of the cart, because I've got all these other things going on. And it's your job, as a Lyapunov function expert, to make sure that those two things don't interfere with each other too much, and you still achieve the task. The language of Lyapunov gives us that power, okay? Even more so these are not going to be global controllers. There's going to be some methods of, some values of k that work. So once I put those coupling terms in, and they do start fighting, in our simple case for just the pendulum, for any k that was positive, we achieved success. I always went downhill. But now that I have these terms fighting, there's actually only a subset of k's, k1, k2, k3, for which those coupling terms fight each other appropriately and you still go downhill. Lyapunov will tell you all of that. It's more algebra than I want to do on the board, but it's straight through, you know, it's almost just square everything and put it to work, okay? So, you know, so Philip, you asked a good question last time. You said, so we said that we have this proof that v dot's going downhill, which says it's going to stabilize the total, you know, the largest invariant set, which includes the homoclinic orbit, but also includes this. And you said, how do I know it doesn't go to this? It goes to this. And, right, so there's more work we can do. In fact, v dot going downhill means I'm driving this way. And remember our region of attraction type ideas here, right? So even my simplest example like this, it was the same story here. V dot was 0 here. V dot was, you know, negative inside here. V dot was 0 here. But I could say, by virtue of being inside this bracket, I could actually estimate the region of attraction of this fixed point. And for the pendulum controller, it is actually the whole state space except for the origin. So you can do more. It's true that the Lassalle's theorem only says you go to the total combination of fixed points. But for any one fixed point, you can then look about its region of attraction. Okay? Yeah.
Yeah. So for I guess the end game of this control, once you reach near going up and near the center of X, for switching to the LQR, would you have to make sure that you're in like the 4D boundary?
Yep.
That is like if you're near the top but you're still moving on X, you can't give up yet.
Correct. Right. And so and we're going to compute that. We're going to write an algorithm that will compute when it's safe to do that in the next lecture. So yes, exactly right. So if your cart was moving at a very high velocity, even if your pole's at the top, you might not be safe to turn the LQR controller on. You want to be in the place where the linearization is good, which is closer to the 4-dimensional fixed point. Okay, there's another virtue, maybe virtue of these controllers, right? I kind of joked about it last time. It's easy to type in, okay? But if you can contrast that with, for instance, the dynamic programming solution, which is a huge tabular representation, right? Which is, I mean, it's not hard to write in a vector or times or whatever, but it's not interpretable, right? This is like a small, easy to write in, couple cosines, couple theta dots. I can tell if it's ever going to blow up, right? Roughly speaking, this is the last time you're going to see that in this class. And I consider it one of the shortcomings of the field, honestly. If you ask me in general, for a more general problem, to come up with simple controllers, I don't know how to do it. Once we flip to the optimization machinery, the things that would come out are less simple, right, in general. And I think there's a standing challenge. Well, I don't know if it needs to be simple. I've gone back and forth in my own sort of philosophy on this, right? And so there was a time where I said, if once we really understand things, we'll turn a crank and, we'll run an advanced algorithm, and the thing that will pop out on the other end will be something beautiful and simple. Like if we've really written down the right algorithm, then something like this should pop out. I don't know if that's true anymore, right? So I do think that the robustness that this has to mass and friction and other things is desirable. And I still think that when we turn the crank, the right crank, the thing that will pop out should have as good robustness properties. I don't know if it's important for it to be written down on a blackboard or not. You know, I think I think deep representations, deep networks and other things have challenged whether simplicity is equal to complexity or beauty, okay? It might be that the number of parameters could be very high, and that's okay. So we'll see. But I long for having something like this pop out of an algorithm, and I don't have much to say in that direction. Okay, PFL, energy shaping, connects to Lyapunov. I hope that story's, pretty clear. Okay, so let's take the other big idea in this space, which is differential flatness. So, for cart pools and acrobats, partial feedback linearization and energy shaping has been the story. It's sort of like that's the big story in those fields. Quadrotors I put in the same set of lectures, but and LQR works for both of them. But quadrotors are actually so easy that actually LQR works for a big range of initial conditions. I remember, and I actually, if anybody cares, I went through and made sure that you could, in the source code, that there was a cute little full-on Python quadrotor 2D thing that you can play with. Oops, I was building right before this. Maybe I shouldn't have done that. Well, okay, I won't mess with it now, but my little silly matplotlib quadrotor is all fully Pythonic and in the source code now. Okay, and it looked like this, right? I have my little silly propellers, which are just a figure 8. Okay, the coordinate system here is x, y, with this being theta. There's a parameter here, r, and it's a total inertia, I, and a mass. Okay, gravity's going down. I have 2 control inputs, U1 and U2, which are just the force being generated by the propellers. Okay? The equations of motion of this are almost trivial. I have mass x double dot just because it's a single body. X double dot is just U1 plus U2 minus sine theta. U1 plus U2 cosine theta minus mg, and then I theta double dot is U1 minus U2, because this one's torquing it this way, this one's torquing it the opposite way by the moment arm R. Okay? If you take and try to apply LQR here, with basically certainly with no limits on U, but even with sort of what you can get in a quadrotor today, this thing stabilizes from basically all initial conditions. You can flip it out, and it'll just balance, right? And people do that with real quadrotors, and I'll show you some videos. Okay, so energy shaping sort of isn't a thing for quadrotors. You don't need that. What people do instead is they try to make them fly through hoops and do stunts, right? And play ping pong and other things, right? It turns out the same idea of you get to control a few things matters for quadrotors, but it's a different version of the same of that idea, which is called differential flatness. Okay, and most of the time when you see differential flatness, you go from the word differential flatness to being completely mired in algebra, and sort of it's uninterpretable. So let me not write the actual definition, mathematical definition yet. Let me just make sure the intuition is clear. The basic idea is that because my system is so constrained, it has less actuators than degrees of freedom. If you pick a few variables, pick my z equals hq again, let's say. If I give you a trajectory in z that you'd like to follow, it might be, if you've chosen z well, and the properties of differential flatness tell you how to check, that in order to follow that trajectory in z, it tells me exactly what every other thing in my system has to be doing. That u is completely defined, and even the other degrees of freedom that were not directly implied by z are completely defined. Okay? So it could be, the picture you'd like to have is that a trajectory in my output space, whether it's the location of the pendulum, for instance, if I define some trajectory in that output space, then there's a one-to-one mapping with what must be happening for that to be true in my x of t, u of t. If you have that property, then you've got differential flatness. Okay? So let me give you an example here on the planar quadrotor. It turns out, if you tell me what x and y are doing over time, then that's enough for me to tell you exactly what u had to be and exactly what theta had to be. Right? You've got two actuators, you get to control two things. Let's just pick a trajectory of the center of mass over time. We're going to make it fly around the room, okay? There's only, once you tell me that trajectory, there's only one solution, well, okay, for the most part, you'll see there's a tangent in there, okay, but there's basically only one, so you can pick the logical solution where you stay upright. That implies something about what theta had to have been and what u had to have been for the entire trajectory, okay? So let's say, in this case, z equals just the x, y position of the quadrotor. So it turns out that my claim here, specifically, if you give me for all t in at least some window here, x of t, sorry, z of t, my output variables, then that implies x of t and u of t over that same trajectory. Now, I'd like to additionally require, this must be differentiable four times, actually. You got to be able to, I want it to be C4. Okay, so I want x double dot, right? Four times differentiable for this to be true, and we'll see why. Okay, so you can't just pick you can't pick x going like this, right, and have these corners in it, because I won't be able to find a solution that satisfies that. Okay, so how can we see that? How can I convince you that that's true? So first of all, if I just look at these equations, let me convince you that just by looking at z and its derivatives, if you have to give me the whole trajectory, right? So I'm allowed to look at the derivatives. So if I know x and y over time, then I can figure out what x double dot and y double dot were at any instant of time. And if I write negative mx double dot over my double dot plus mg, okay, I'll just take these two equations, then what do I get? I get u1 plus u2 sine theta over u1 plus u2 cosine theta, which is just tangent theta. Okay, so just by virtue of you telling me what the center of mass had to be doing, if I look at the accelerations that that center of mass is going under, it tells me what angle the quadrotor must have been at to accomplish that. Because there's not enough motors to do more. Right? So, I mean, just the smell check here. So if I have X and Y, if I'm here and I just say go straight up, then that would be X double dot equals 0. So tangent theta equals 0. It's saying theta has got to be horizontal, right? If you only told me I'm going to go straight up at a constant acceleration, then that would come back with a solution saying theta should be 0. Okay? Maybe more interesting would be, what if you told me I want to be going like this? So y double dot equals 0. What's the solution going to look like? If y double dot equals 0 and let's say x double dot is a constant, can you work it out?
It's the ratio of voltage, right? It's that and the acceleration.
Say it again?
It's the ratio of x double dot over v, so the acceleration this way over the acceleration, the fourth gravity now.
Yeah. So, exactly. So, you get the arctan, or the, inverse of negative x double dot over g. It's not, so it depends on the mass over the, it depends on acceleration. So you're going to get a quadrotor that's sitting something like this, because it has to be able to produce enough vertical thrust to be fighting gravity in order to stay on that line, okay? But enough horizontal to be going at that desired acceleration. And there's a unique solution to that, right? Which is some angle like this. And that comes right out. Okay, so if you were to draw any smooth trajectory, there's no kink there, smooth trajectory here in this z of t, then there's a unique solution to what my quadrotor has to be doing based on the accelerations of that curve. Furthermore, the control inputs are completely specified, right? So in order for this to satisfy all the equations of motion, well, maybe an easy way to see that is I could differentiate. Once I have this relationship, I can differentiate this twice to get what theta double dot has to be. That's where the fourth order thing comes. It's going to be some function of all the way up to dx to the fourth time derivative of x, because if I differentiate this thing twice with respect to time, I'm going to get up to x double dot, 4 dots, right? And y, okay? But then once I have that, I have two equations and two unknowns sitting right here, and I can solve for what u1 and u2 have to be. Completely. Okay? So knowing z, when this is your choice of z, completely specifies what everything has to be doing on the quadrotor. In practice, this is just telling me that I know what u of t, u as a function of t should be along that path. There's extra work to stabilize that path, to make sure that if there's small differences in initial conditions, you'll still return. But to just execute the path, this is everything, okay? Same idea. You're only going to be able to do this if z is the number of actuators you're asking for or less. But in practice, it's only going to completely prescribe things when it's the number of actuators you've got. Okay? Now, the full-out definition of differential flatness, in general, z could be a function of my, if I have x dot equals f of x u. You're allowed to pick z to be any function of x, u, and also the time derivatives here. You can actually pick the u dot as to whatever order you'd like. Call it kth order. And the resulting controller the resulting trajectory that you get, you have to be able to get back to just from looking at z and all its derivatives, z dot, it should actually be the same order here. You have to be able to completely specify x. Similarly, you have to be able to completely, just only looking at z, be able to completely specify what u is as a function of time. If you can find a z for which this holds, and these mappings, then you say your differentially flat system is differentially flat in z.
Why is it called flat?
There is a topological sort of motivation for that, but I can't give you the, it's about the, being a smooth function of these high order derivatives. By the way, do you guys know what this is called? What x, the x to the fourth time derivative is called? Jerk, right? Position, velocity, acceleration, jerk, and then snap, crackle, pop, if you keep going. Really? That's true? Okay. So, physicists are funny. But we're going to get that in a second here. So, the 3D version has had huge application on real quadrotors, okay? Most people don't care as much about controlling matplotlib quadrotors in the plane. They have to do the 3D version. The flat outputs of choice are x, y, z of the center of mass plus the yaw angle. Yaw, right? The one, it's kind of the one you probably don't care about, right? If the quadrotor is sitting here, that's pitch, that matters a lot, right? That's roll, that matters a lot. The yaw, you think maybe shouldn't matter so much, but these are the outputs that people know to be flat. If you specify these for all of time, then it implies what your pitch and roll had to be doing over time, and what your propellers had to be doing over time. Okay? So this is this was a Mellinger and Vijay Kumar paper from 2011, I guess. Right? The reason I wanted to make sure you knew what snap was and jerk is, right? So in the derivation's almost the same. It's a little bit more complicated. The reason you need, so first of all, the 3D quadrotor model, when you write it down, if you only do the free body diagram the way I did for this, then you get a system that you cannot stabilize at the top even. The fixed point is not stabilizable, and it's also not differentially flat. In order to make the system controllable at the top, you have to include one more effect, which is the fact that when you spin up your motors and apply a torque, there's rotor inertia, and so there is some coupling in that causes yaw when you spin your actuators. If you don't have that, then if you just think of them as pure force sources at the four props, then actually you don't have the ability to control yaw. Okay, so the quadrotor model, to make all this work, requires that rotor inertia in it. Otherwise, it's almost the same as the free body diagram. Okay? So then, given that, you specify those 3 variables, you get a second derivative of, in order to compute these variables, you need to get positions up to the 4th power, which is jerk. And in order to make nice trajectories in all those variables, you'd like to have smooth jerk, which you can achieve by doing minimum snap. Is that cool? So in order to have smooth jerk, you'd like the derivative of jerk to be small, and the derivative of jerk is snap. So the optimization is over keeping the 5th degree derivative of position over time small. Yeah?
So is that hard or not?
Say it again. Oh, did I say it wrong? Yeah. So I'm sorry. So it is jerk is okay. Yes, I'm sorry. Position, velocity, acceleration. Jerk is 3rd. 4th is snap. Yes. So I must only need 3rd here. Yeah.
It's the index from 1 you're looking at.
Say it again.
Index from 1, right?
Oh yeah, exactly. I had a MATLAB bug. That's actually possible. So I used to write all the code in MATLAB, so I do make that bug mistake sometimes. Okay. So there's additional work here so now if you want to, think about trajectories which are smooth over x, y, z, and theta yaw, but let's say do something cool like fly in a figure 8 or fly through a window or something like that. We can use optimization at this level, but it's easier because I can execute most trajectories in this level, maybe not the one that runs into the wall, but most trajectories here. And then I can just map that into the implications for the whole quadrotor. We'll talk about the planning, the optimization of those paths later, but let me just show you that this works, and this is how Daniel and Vijay and a bunch and people that followed have done some really cool stuff with quadrotors. Okay, so this is
This video presents autonomous control capabilities for a quadrotor helicopter. We use a 20-camera Vicon system and an onboard IMU for state estimation. Here we show single, double, and triple flips. We developed a method for flying to any position in space with any reasonable velocity or pitch angle. We use the method to fly through windows at various angles. Here there's less than 3 inches of clearance on all sides of the quadrotor. We also fly between other quadrotors. The same method can be used to descend or ascend through a horizontal slot.
pretty awesome, right? And it's actually leveraging the idea that quadrotors can't do
By
arbitrary
placing
trajectories.
Velcro on the bottom of the quadrotor and on a target, the quadrotor can perch on a surface.
It makes planning easier.
Here we demonstrate perching on an inclined surface.
My favorite one is actually this.
We implemented an autonomous controller capable of recovering from extreme initial conditions. We can precisely track trajectories with large accelerations and velocities.
This is my favorite
We
part.
developed a method for generating trajectories to optimally fly through any number of waypoints. We can quickly generate trajectories to react to dynamic objects.
That's awesome. I mean, I don't know how many takes it took, but that was pretty awesome, right? Because and really what that says is not only that they're controlling well, but they can plan fast, right? And planning fast is because they're just picking simple trajectories in here that are smooth, and then they were using differential flatness to map that into the whole thing. Okay, yeah?
Are hexacopters also differentiable?
Say it again?
Are hexacopters also differentiable?
Should be. I don't know that result, but I mean, you should be able to control all 6 degrees of freedom in the hexcopter, and I don't see why a trajectory there wouldn't imply the everything about the quadrotor or the hexrotor, but I don't know. I haven't actually written it down. In general, the tools for differential flatness are less. You're still in the game of, like, there aren't algorithms that people know or talk about that say, given some h, how can you check that there's some way to write down here? There's still a manual step of running through the algebra and finding the recipe for backing out x and u as a function of the derivatives. I don't know of a numerical recipe for checking the flatness property of a given thing. Instead, when somebody figures it out, they write the paper, and now it's in the tome of knowledge and people use it, which is how nonlinear control used to be more generally. Okay, so the big ideas there are, and we're going to move on to the next sort of class of algorithms and systems, but in these acrobats and cartpoles and quadrotors, I think they're canonical underactuated systems where we can teach a lot, we can fall back to a lot, and to make sure our algorithms work. But the key idea here is that you've got M actuators, you get to control M quantities. They could be exactly joints, or they could be something more task general. And in the partial feedback linearization case, that can lead to stabilizing controllers, especially when coupled with Lyapunov. Or in the trajectory case here, it can be that trajectories of those M coordinates can imply trajectories for the whole space. That's sort of the opposite way to leverage that idea. Okay, we'll do computational Lyapunov next week.